Hi everyone, in this video we will look at line integrals in space, which means instead of the two-dimensional coordinate system that we were dealing with earlier, we will now deal with a three-dimensional system. So a curve in space can be parameterized as a function of time t as xt, yt, and zt. The line integral changes pretty much according to how we saw it in two dimension, where the line integral of a function f x y z over a curve c becomes f expressed in the parameters, so xt, yt, zt, and you have this arc length sort of term once again, dx over dt squared plus dy over dt squared plus dz over dt squared. Now, there's a concise notation that this can be phrased in, which is the following. It goes a to b f rt and the absolute value of r prime t from Calc 3, if you remember that this expression, the square root, is the position derivative, the absolute value of the position derivative vector. And in a special case where your function is constant, which equals 1, then this L is the length of the curve. So basically saying, once again, it's the same thing as with density. If we say the density is constant and is 1, it means it's uniform, and when you do the line integral, you get a physical quantity, which is the length of the curve itself. So how do we find this? Well, it's pretty straightforward. We write the function in its component form and express each of them in terms of the parameter t and perform the integration. Let's look at an example that will make it clearer. Oops, wrong. Evaluate this integral where c is the circular helix given by the equations x equals cosine t, y equals sine t, and z equals t. So recall this is something we have seen a few times in Calc 1, Calc 3, sorry, where this particular equation gives you a helical structure where the circle comes from cosine sine, and because z is changing with time, it's traveling up in the z direction. Right, so according to what we had above, right, all we have to do here is we have to rephrase. So we have this is y sine z. So in terms of the parameters, which is cosine, sine, and t, this simply becomes sine t, which is sine squared t. What else do we need? We need dx over dt, which is negative sine t. We need dy over dt, which is cosine t, and we need dz over dt, which is 1, so that this entire square root term, dx over dt squared plus dy over dt squared plus dz over dt squared, is simply sine squared plus cosine squared plus 1. And sine squared plus cosine squared again is 1. That's the most common thing we see. We get root 2. So the line integral over the curve c of y sine z ds simply becomes the line integral as t goes from 0 to 2 pi, because that's what the limits are, f of cosine t sine t, which is sine squared t, times the square root stuff, which came out to be square root of 2. And now in dt, what we have is we're back to our old pretty common integral where we rewrite the sine squared as 1 minus cosine 2t which means we have root 2 over 2. When you integrate this, you get a t minus 1/2 sine 2t from 0 to 2 pi. This second part becomes 0 because when you plug this in, you get sine 4 pi minus sine 0, both of which are 0. So it's really just the first part we're concerned with, root 2 over 2 and a 2 pi. 2's cancel, so the whole thing comes out to be root 2 pi. And that is the line integral. So this is the case when we are doing the line integral with respect to the arc ds. Now let's look at another example where the line integral is broken down. It's not with respect to the arc length ds, but it's broken down in different directions, broken down into dx, dy, and dz. In this case, we are asked to evaluate this line integral over C. Now, similar to two-dimension, C can be a combination or a union of a bunch of smooth curves, in which case we just find the values for each constituent curve and add them up. So C is a line segment from 200 to 345, followed by a line segment from 345 to 340. So we have a 3 space here. We have a point that goes X, Y, Z. We have 200, so that's over here. From 200, we go all the way to 345, so somewhere here. Then from 345, we drop down to 340, which means it's on the XY plane. Which means our C is now made up of two curves going C1 and C2. And that's all right. It means we just have to find the equations for each of the line segment that will give us the parameterization. And then evaluate the line integral over C1 and then over C2 and simply add them up. So first we need the line segments in parametric form. To do that, we will use this. RT is 1 minus T R0 plus T R1. So going from, we have a name, so let me just call it C1. So C1 is going to be RT 1 minus T from, vector notation, so let's do 200 plus T, vector notation, 345. So that comes out to 2 minus 2T plus 3T, 0 plus 4T, 0 plus 5T, which is 2 plus T, 4T, 5T. So that's X, that's Y, and that's Z. So the first integral over C1 becomes, okay, let me write it. It's the problem was y dx, z dy, and x dz becomes an integral from 0 to 1 of y, which is 4t, and dx, which is dt, plus z and dy, which is 4, if you take the derivative of 4t, dt plus x, which is 2 plus t, and the derivative of z, which is 5, dt. And this becomes a straightforward polynomial integration. So what we get here, let me do one more step. You get a 4t, a 20t, and a 5t, which is 29t, and a 10 from here. So this is 29t squared over 2 plus 10t 0 to 1, which becomes 29 over 2 plus 10, 49 over 2, 24.5. So that's the line integral for C1, the first part of the line segment. Now there is a second line segment. For the second line segment, we go from 3, 4, 5 and we end up at 3, 4, 0. So let's find the parametrization. This is now 3 minus 3t plus 3t, 4 minus 4t plus 4t, and 5 minus 5t plus 0. This is 3, 4, and 5 minus 5t. So a lot of the terms here will become 0 because x is constant, y is constant, so dx dy is going to be 0. So over C2, y dx plus z dy plus x dz is 0 to 1. This will be 0. This will be 0 because x and y are constant. And this will be 3 and dz is negative 5. So this is 0 to 1, negative 15 dt, which is simply negative 15t to 0 to 1, which is negative 15. So over the curve C, this particular line integral is 24.5 for C1 plus negative 15 for C2, which ends up being 9.5. Okay, so we'll end this video here. In the following video, we will look at an application from physics, which is in work done.